Hello everybody and welcome back to this series. We are still trying to write an operating system from scratch. Last time we've started work on GDT redefinition, but while I was editing the episode, I've noticed that I've made quite a few bad choices. So today we are going to right the wrongs and then maybe take a look at some IDT stuff. Alright, let's get to it. Alright, so last time we were about here, we've made this absolute Frankenstein of a struct here, and I actually was wrong about a few things. We did not need the actual physical address. LGDT LGT here does take the linear address. I've double checked that on the Intel documentation, as well as I've made quite a few mistakes while creating the struct here for descriptors. So let's right those wrongs. So first of all, this system boolean here should actually be descriptor type. Should probably create a type for that. Whoops. And of course, yeah, we should change this as well as descriptor type. Right, so this one should change too, and so there's this one. And I guess we could do the same here for the 16 bytes descriptors. So descriptor, perhaps no underscore there, descriptor type. Right. Whoops. Descriptor type, this one too. Is there something I'm missing? Yeah, there is something I'm missing here. This one should be descriptor. There's a P missing. Cool. So with this done, I think it's about time we've created the descriptor type thingy here, and also, well, we'll see what the values are for that. So let's take a look at the documentation for that. I think it should be somewhere around here. Yeah. So what the documentation says is that S is descriptor type flag, and it determines that the type for the descriptor, and it says that the type is system segment if it's clear. Otherwise, it's a code or data segment if it's set. So let's do that. So public const descriptor type is an enum for a U1. Let's do this, and here we want a system. This one is if it's cleared, and code or data if it's set, I believe. Double check that. Yeah, that looks about right. Okay, so let's go here, descriptor. Cool. Wow, so that's this one. Right, so here we want this to be just clear by default, and here we want this to be code or data for our create function here. This one should be fine. This one here would need to be system, otherwise we'll have a build issue, and this one would be code or data. Very nice. Another thing I've actually missed while doing this last time is the default size flag here. If we go down to the length flag, or what we called a 64-bit. Here at the very end of this, here, if the L bit is set, then the D bit must be cleared. So we should not be setting the D flag. So this what we call size. Actually, I'm tempted to rename this to default size, just so that we can get default size. So let's see here. This one also, and this one has already been renamed. Cool. Let's do the same for. Let's do the same here, as well as here, and yeah, we should have 2 of these here. Cool. Right. So now what we need to do to add here is probably just at the start of this, do something like start debug assert so what should we assert? We want args.is64-bit and args.default size is different from 1, or not args.is64-bit and args.default size. No, actually, just this would be enough of a check. So if this one is set, this one needs to be 0. Actually, let me just make this a bit more transparent, what we mean here. So this set and this 0 would be our first assertion. Otherwise, this not set gives us the right to choose whatever we want for default size. Cool. So let me just move or copy this over to here, and that should be pretty nice, I think. There's just one thing I've just seen here. Just gonna get rid of this. We haven't used the 16 bytes descriptors yet, but should keep them maintained, I guess. This absolute monstrosity here, I want to get rid of. So how am I going to do that? Let me first of all, let's think for a bit. Yeah. Okay, so here's how I want this to become. I want this to become as simple as can be. I want to have a so set my GDT entries here, entries, and then I want to call load. How do we go about this? Should we create an ASM module? Assembly module dot LGDTR that takes the LGDT GDT address, I guess. Sure. And then we are going to need to do something that we forgot to do actually last time, which is actually set the segments to use entries in the new GDT that we've set. And how that would go is we would need to load the data segments. So we need to do a bunch of move selector into DS and FSGS, etc. Right? And then we need to also do a to set the code selector by doing a long jump with the correct selector. Yeah, so something like L jump to some. I'm not sure how to do this in AT&T syntax, but I guess it would be something like 0x code selector my address here. Address in just normal. Actually, it would be something like this. In Intel syntax assembly, we'll try to see how we do this in AT&T syntax. And that means that here I want to set my GDT entries locally in this. Since I don't need to allocate memory anymore, I'm gonna get rid of this dependency here, which is weighing us down more than anything else. And that means that I'm going to have in this module here just floating around a sort of comp time array, or rather just a const size array. Let's call this max GDT entries. And this would just contain our entries, and then we'll have GDT register, I guess, which would be the would have the limit and the base here. So this is the plan. Let's execute. Okay, so let's first then start by creating a const. Let's call it GDT, and this would be just a struct that would hold all our GDT stuff. And here we are going to define var GDT entries entires, which would be defined as, actually we need a const max GDT entries. This one we can just set to 5 for now. It would be comp time end. This one here would be max GDT entries, of course, of type segment dot descriptor segment 8 bytes. Okay, so here we are running into a sort of problem. We would like this to be, okay, hold on, let me just set this to undefined first. We would like this to be sort of a combination of 8-byte segments and 16-byte segments, since we are going to need to set 16-byte segments for our task state stuff, or our task descriptor stuff. So how do we go about that without breaking everything? I guess we could break down the 16-byte tasks into two 8-byte bytes. Otherwise, how do we go about this? I guess we can, if we wanted to, we could allocate these as just straight up U8s, just a buffer of bytes, and write to it ourselves. That also could be a an idea, I guess. But for now, actually, let me just add the alignment constraint here. So the documentation here says, if I can find where it says that we need the base address to be, where they put that. So they basically said, you're gonna have to take my word for it, that the base address of the GDTR thingy here, so this base address here, needs to be 8 bytes aligned for optimal performance of the CPU, except that we have this limit that comes right before that. So that means that we need to allocate something that has a And limit is, of course, 16 bits, so 2 bytes. So this one needs to be on a 2-byte boundary, while this one here needs to be on a 8-byte boundary. That's a bit of a head scratcher. I'm just going to go for a 16 bytes alignment and hope for the best. So align 16. I guess, yeah, this should come here, and I guess that should make it happy. Cool. So let's, for now, go with this, and I am going to just try to... yeah, you know what? Let's be a bit, just tiny bit forward thinking, okay? I'm just going to go for this. I'm just going to say size of was that segment dot descriptor 8 bytes times max GDT entries. And if we, for example, have max TSS entries, let's set those to 0, but we can, for example, add that here. So add size of segment dot descriptor 16 bytes times max TSS entries. Yeah, we can have those there. We can also do something like stud mem zeros, I guess. No, this one takes a type. Yeah, never mind. I guess we could do something like this 0, and then we can probably do something like this max GDT entries by size, or just size is this. Probably remove those, and then here we can go ahead and do GDT entry size. Of course, this one needs to be a U8. Cool. So here we have initialized those. So I guess I'm just going to create a public function in it that would take nothing as arguments. We are just going to try to create slices from that. So const GDT entries, let's call it slice for now, and then this would be so GDT entries. Can we do that mem slice from bytes, or slice bytes as slice? Okay, that's good. That is good. So we want this to be a comp time, of course, of segment dot descriptor 8 bytes, and we want the bytes to be GDT entries, but we want them from 0 to size of segment descriptor 8 bytes times max GDT entries. How about that? And I guess this one returns void. Okay, so if that is okay, that means that now we have a number of GDT entries here. We should have 5 of them, since that's how many we've created. And here we can go ahead and basically copy these. Yeah, and let me just go ahead and do let me just do this. So this one would be GDT entries buffer. Sure. And here I'm just gonna repaste these and go ahead and do GDT entries here. Very nice. Cool. So now we have our GDT entries set. I'm just going to remove all the sizes that we've set because these are bad. And I am going to... I guess that's all I'm going to do. For now, that should be enough. Right. So, do we have a GDTR? No, we've created here, but we've never used it. And actually, now that I think about this, these are, these are inverted, but okay. Never mind. Right, so let's do const GDTR, which would be a struct, a backed struct. Sure. This back struct here would be, well, just limit, I guess. This one is always a U16. And then we have a base, and actually, the base can have a U64 in it. Let me just double check here. Yeah, in 64 bit mode, we can have 64 bits for the base address. That should be okay. Okay. Right. So that's fine. And that means that here we could go ahead and create, I guess, var GDTR, which would be type GDTR, and this one would be, I guess limit would, limit would need to be size of GDT entries buffer -1, and base should be the address of GDT entries buffer. Okay. I'm not sure if this here would build. I'm not sure if it's going to build correctly, but we are going to try to see. Right, so here we have all the entries set up. So we need to basically do flush. How do we flush GDT? I guess. And here we are going to need to create a function flush GDT, and this function here would do very simple things. This language needs to have a return type. This function here would need to do very simple things. So first of all is let's create a segment selector. So let's see here, segment selectors. Okay, so I guess we need to describe this struct somewhere. Segment seems like a good place where to put this. So const selector is backed struct. Yeah, sure. Backed struct. Backed by, how big is that, a U16? Of course. And here, let's see the bytes. So bytes 0 and 1 are for the privilege level. So we already have a privilege level. Privilege level, I guess. Or we call it just privilege, I think, in the other things we've created. Yes. So privilege level. And I guess we could set this by default to ring 0. And then what's the next byte is the table indicator. So table indicator, and this one here is of type table indicator. I'm not sure if we're gonna ever use table indicators anywhere else. So let me just declare it in line here. So we have GDT, which should be 0, I think. GDT is 0 and LDT is 1, although we don't really care. And this, of course, would need to be GDT. And then we have the index, I believe. And the index is 12 bytes. So let me just see if there are any things that we need to be wary of. No. That looks okay. So the index is basically the offset into the GDT or LT array. So yeah, I guess that should be fine. So 12. And this one has no default value, so we need to set one when we create it. Okay, so let's go down here. Let's create our segment selector. So we'll have 2 of them. We'll have code segment selector, which would be a segment selector, and this one would have index equal to. So this one is our kernel code, so it's index 1. Let's see here. Index is 1, and then I guess we could just do this. Code goes to data, and the index here would need to be 2. What is the problem here? Oh, yes, of course. This one needs that. Cool. So now that we have our 2 segments, we are going to need to call. So we should probably think about creating any ASM module. Import ASM.sig. I guess we could call that. Do we already have an assembly module? No. I guess we just created ad hoc modules for every instruction we needed. I'm not sure how good that is. No way. Do we have to call this assembly? Sure. So that means that here assembly dot I guess we can call this load load code segment. Code segment. Sure, that's an okay name. And to that we are going to pass bitcast code segment selector, I think. Sure, that looks like a good thing. Data segment, and actually let me just load the data first, and then the code, because I think the code segment is a bit more finicky. So let's do the data first. Right. So here now our init becomes fairly simple. So we need to create a const GDT of type GDT, right? And this one just needs to be initialized like so. Yeah, And then here we need to call into, gdt.init. And that's pretty much it. I guess. So it says we have a problem here. Oh, right, because we have duplicate this entry here. But the good news is that now we can actually just remove all of this. Get rid of all of that clutter. Right, so now that we have these, we can actually just go ahead and let me first of all do... okay, never mind. We should be good to go. So let's create our assembly module. Actually, you know what? Change my mind. Not create an assembly module. At least not right now. We could always create at a later date. So here, this load code segment gets a code. Let's give it just a segment selector, which should be of type segment dot selector. It returns void. And actually, I want to start with data, as I said before. And here we want this to be, so let's just do that. And we want this to be load data segment with data segment selector. Cool. So ASM here. And the things we are going to do are, or rather is, just go through all of these segments here, all 5 of them, and set them to the value of our selector. So we should first of all move our so we want this to be selector, or rather, let's call this data segment selector. Sure. So in this, it's inverted. So yeah, this is the source, and then we put it into some destination to some register, I guess. Or we can actually just ask for this to be already in a register somewhere, selector. So we put this into, I guess, DS. Sure. And then we get this 4 more times, and then we go ahead and... So what are the other letters? ES, FS, GS. So ES, FS, GS, and SS. Right, so no outputs. The inputs are DS selector. We want this to be put into a register, and we want this to come from at bitcast as U16, sure, at bitcast of segment selector. Sure. And I guess the register used would already be marked as clobbered, so that should be okay. Yeah, okay, so what's the problem here? With no output, but marked, okay, volatile. There we go. Cool, so I think that should do the trick for now. Let me just double check the documentation for a bit. Yeah, I think we should be pretty okay. Right, so I'm just going to mark this to do check that this behaves okay. The reason is we whoops, let me just do something like this. The reason is that this might have some weird effects we're asking it to go to a register, but I'm not sure how the ZIG or the LVM assembler would interpret that, so we need to take a look at it. Right, so actually, just notice that here we are missing another set of these. Right. Right, so now let's create function load code segment. This one will take a segment selector also, segment.selector, and returns void. Actually, we can add something here. I think we can. Yeah, never mind. I want to do a thing that's a bit complex where I get the selector, I check in my GDT entries table that it's of the actual type we want. So for data segments, we check that it's a data segment. Otherwise, actually, I think it might be worthwhile to do. So debug.assert that so GDT entries. Oh, wow. We don't really have GDT entries, so we need to recreate those. So can we go about this like so? So built-in dot is const built-in is import built-in, and let's see here. Can we check that is test? No. What do I want to check? I guess optimize. I guess target dot no. Okay, I guess we are going to read documentation. Yeah, actually, never mind. It was fairly easy to find its mode, and I guess this would need to be debug. So if we are in debug mode, I want this to. So let me just go ahead and do this again here. And I guess we should do something like segment selector dot index, and here we should check the type. Okay, so I guess we should do something like const GDT entry selected entry, sure, of type segment dot I guess descriptor 8 bytes, and this one would have GDT entries of segment selector dot index. I guess, and we should also do so the debug assert if segment selector dot table indicator is GDT, of course. Oops, there we go. Right, so this one here just becomes selected segment or selected entry dot type dot code is false. Sure. Is that how we define those? Yes, that's how we define those. So we just want to check that this is in fact a data segment. And I guess we could probably do the same thing over here. Just put that there, and this one here should become true. Yeah, okay. Now let's get to the volatile. Let's get to the actually important things here. So we want to do, I'm just going to write pseudocode for now. We want to call or do a long jump. A long jump, I guess, in this should be something like jump with a qualifier. And we want to jump to some offset. Let's call it jump offset. Right. Something like this. So the way we want to jump to this is to construct some sort of jump destination, but I think the easier thing we could do is to actually use readQ, which is just popping things. readQ would basically do a pop from the stack and then a jump to that address that it popped. And then if we actually can get ourselves to put the correct selector and address in the correct place, I think we could make this work. Right, so let's first, I guess we should push Q. No, let's first start by moving our, I'll call it CS selector. Sure, let's put that into AAX or RAX, I guess. Before I forget, let me just do this and add, wait, hold on. So outputs, inputs, clobbers, right. And I guess there is some sort of new syntax that I don't know of, but just going to do this for now. Okay. Right, so now that we have this, we should go ahead and do push Q, or they have that here. We are going to push RAX. So this here, we are pushing the selector in onto the stack. Then we need to get the offset of our jump here. And I guess for that, I'm going to use load effective address with a qualifier. And I'm going to use the offset as the offset of LEA, and the register to which we are offsetting is the I guess instruction pointer, so RIP, and we are going to set that into RX to reuse it. And I guess here I should push Q RX, and then the jump Q should pop the address and the selector here. And since it's a long ret, so if we just had readQ or ret, it would just pop the address from the stack. Since we have set this to long readQ, it's also going to try to pop the selector, which is the second thing we've put onto the address. And this actually is the relevant part of the documentation here. It says that we basically pop from the top of the stack the instruction, the return instruction, and put that into the instruction pointer, and then we pop the segment selector and put it into CS. Of course, this only works for far returns. Short returns or near returns just have the instruction that gets popped, basically. They do not expect a segment selector. And I think that's one of the few ways that we can affect CS. Maybe it's the only way we can affect CS. Okay, so let's finish this up fairly quickly. So load code segment with code segment selector. Right. Okay, so I guess that's all the refactoring I want to do for the GDT. And truth be told, it's looking quite a bit better than what it was before. It's quite a lot simpler now to work with. Right, so one thing we have not touched on yet is actually loading the GDT, so load GDT. And this is something we've already done before, so I guess we can just go ahead and do that. So load GDT. This one takes nothing. I think we should have all we need here. So volatile assembly, and here we should just have so lgdt with as value so gdtr, I think is what we've called this. Yeah. That should be fine, right? There should be a constant. There should be a variable. Okay. And so no outputs and inputs would be just GDTR. And that we get as a, we don't really care, from GDTR. Yeah. The thing I'm unsure about is the order of initialization for these things here, but we'll take a look at that shortly. For now, let's check that this builds first of all. So I guess make be all, and of course it does not, because we have not changed the use here. This does not fail anymore, and this should be okay. Right, so what does it say? No field or member named init in descriptors GDT. You must be joking. Why is that? Oh, I see. I see why that is. Okay, that's actually pretty... It's not bad. I think that fixes it. Right, so exploited U8 but found 40 of them. Well, yeah. 117 or 177. What is the problem here? Oh. Wait, what? Oh, okay. GDT increase size. Misinstruct field default size. Right. Yeah, okay, I see it. I see it. We've actually just deleted that. Default size should be 0. And this should go here, here, and here. Okay. Back in integer type has size 16, but struct has size 15. What? Oh. Quick maths. 179. Expected type, but found. Oh. So len. Sure. Expected U64, but found pointer to okay. I guess pointer from or rather int from pointer. Sure. Oh. I think we can cheat our way through this. Can't we not? Can we not? So I guess we could do something like so. GDT entry size of U16, line 16. Yeah, the pointer would have the alignment, that's fine. You cannot assign to constants. Yes, that is obvious. Var. Expected type GDT, but found empty. Yeah, okay, so that's not good. That's starting to become a problem. So I guess this would need to return this, but yeah, okay, so no. This remains void. We are just going to extract anything we need outside. Yeah. So let's think about this for a bit. So I wanted to package this nicely into this GDT struct here, but it looks like it's going to be quite hard to do. Actually, let me think. No, actually, I think we can do this. Right, so this returns this, and we should return yeah, sure. So if we get rid of this, and probably this too. No, hold on. This can stay. If we get rid of this and set this to something like so, and we get rid of this and go do something like this, I think we should be okay. Because here we can just do something like this, or rather, no, hold on. We should create var GDT is, this should be of type GDT. Yeah, okay. Okay, and that means that this GDT entries here would need to be, so GDT dot that buffer. Yes, okay. Okay, that's looking good. And then I guess this here is now impossible. So I think we should just go down here and do gdt.gdtr is, and we probably just need to copy these, shouldn't we? And we should just prefix them with this. Whoops. And that should work. The only problem is that now all of these would need to take a pointer to this, so that we can do self.thingy. Same goes here, I think. Let's think about this. So gdt.flush.load at gdt.flush. Sure, so this one here would also take self pointer to this. And we should do self dot and because these here do need self. Yep, okay. That's I'm convinced of this. Right, so this one here goes gdt dot rather self dot thingy. Yeah. So does this one here, self dot thingy, and we need to put self, which would be a pointer to this in here. Cool. Cool. So now that this shows the declaration of GDT, okay, so how do we go about this? Yeah, I don't know. Let's just do this. And of course, here at the very end, we should return GDT. There's a bit of a problem here, isn't there? Okay. Here we set in all of the values, setting the thing here. Oh, right. So I guess we should just get rid of the initialization here. Right. So missing field struct GDTR. Of course, we haven't said it. That's fine. Actually, we've said it here. So I guess we are going to do this. LVM unknown input or output name. What? CS selector. Oh, of course. We probably need to give it the inputs. CS selector. This one is just a number. And it comes from at as u16 at bitcast of segment selector. There we go. Okay, slight issues still. Invalid operand for inline ASM constraint. And where is that? If you can, please let me know. Oh, I guess we should do something like this. Or rather, we can do something like so. It's a memory location. Or actually, let's do something a bit more sane. Let's actually yeah. So I guess we need this pointer from int first of all. We need to get the pointer of that. Must have a oops. It's int from pointer. Yeah. And that int goes here. And I should not forget to put this, otherwise it's going to complain a whole bunch. Okay. It does build. Now, does it do the things that we want it to do is the question. And what I'm going to do is LVM obj dump. Do we have something here? Yeah, that's pretty cool. And I'm just going to dump that into let's go kernel dump dot txt or something. Sure. Okay, so nvim kernel dump. And here we are looking for, let's start with load GDT. I guess it's going to aggressively inline this if we are using release. Yeah. I'm going to do this rebuild without release. Expect some integer constant expression. Okay, so now we have even more problems. So let's find where that is. Constant expression. Is this not a constant expression? Actually, first of all, this is wrong. It should be 2 instead of 3. And this is a constant. This should be constant. Excuse me, this is a constant. Okay, so I guess in debug mode this does not work. So let's do something. Let's say that temporarily would like to get this here, set this to code segment selector, and just rebuild this. Okay, so this one does work. So let me just dump this to a file and then kernel dump.txt. And we want to take a look at load GDT. There we go. So here what we have is we are calling LGDT. That's very nice. Right here I can see flush GDT, which was my next stop. And here we just call load data segment and load code segment. Right, so let's take a look at load data segment. Cool. So what are we doing here? I think that here we are checking the debug stuff. So we can ignore that. And here we jump to C3.4, which is after our code. So I guess that's to do the mem bytes a slice things. So that's not really what we care about. What we care about is here we are taking the 16 bits value that's at this pointer here, putting that into AX, and then setting all our registers from AX, which is basically what we are expecting this to do. Cool. So if we go to load code segment, so what we want this to do is load our selector to RX, which is this here, push RX, load the effective address into RX of this value here. So instruction pointer plus the offset to jump offset. And we can see that jump offset is just 3 instructions away. Rather, 3 bytes away, not instructions, bytes. And then we push the value of Rx there, and then we do return for quad to pop the address, pop the segment descriptor here, and jump there. And that should put us back here at this address here. So add RSP with the correct segment selector. We can see here that the segment selector is 8 as a constant value. And if we go back up to where we had our data selector, I guess we should do, oops, not there, load data. In load data here, this, flush, I guess, is what we are looking for, flush GDT. Yes, cool. So here we can see that we have called load data segment by passing it a value, a constant value of 10, or rather hex 10, which is 16. Now let's check that those values are correct. That would validate that we have not messed things up. So here, if I go ahead and do 16 insert 0, oops, maybe I should actually write a 0. Right, so we have 16 zeros, and that's our selector here. We have our privilege set to ring 0, so these 2 bits remain 0. Table indicator is GDT, so this one remains 0. And this one here, starting this one, these bits here are the index. And for the first one, we have an index of 1. And for the second one, we have an index of 2, basically. So this one here is a value of 8. So 8 in decimal and 0x8 in hex. This one is a value of 16. So in hex, that's 0x10. So that means that the values that we see passed around here are the correct values. Very nice. Now, let's bring this back. Make sure that this, so if I go here, I remove this, I jump down here, and I remove, I guess we can just get rid of this with no problems. Let's rebuild to see that it's still working. And let's try to run this. Okay. We do not crash. we do not have any exceptions, we are golden. At least until we debug this and see that it's not the case. But for now, I'm fairly happy with the progress we have achieved. I would have loved to get to the IDT stuff on this video here, but I kind of got nerd-sniped into this rabbit hole of making this a bit more easier to work with. And I think this would give us a fairly nice template to follow for our IDT stuff. So I think I'm happy with how this turned out. Well, that's it for this one. We have went ahead and reworked our GDT things. Not what I planned to do when I started recording this video, but what are you going to do? That's how the flow of things went. As always, if you've liked this video, hit like, subscribe if you're not already subscribed. And if you have comments or thoughts, or you just want to say hi, leave them in the comment section below. I'll see you next time. Fucking out.